So welcome everyone to my talk called Compile Time is the New Const Expert. Today we learn how we can implement compile time sparse vectors and matrices and how we can use them. In case you don't know me, my name is Daniel Wittopf. I work for the German car supplier Bosch, mainly on self-driving vehicles and automated driving. My team is responsible for fusing the sensor data in the vehicle, so we get the measurements from the different sensors. We're responsible for fusing that into one consistent environment representation. And I would also like to thank my colleague Maxime, who had the original idea for the approach I'm going to present today. So some of you might have seen my talk from last year's CppNow, where I was talking about physical units in vectors and matrices. So there, the main idea was to be able to represent non-uniform physical units in matrices, meaning each entry in a matrix can have a different physical unit. And back then, the overarching design principle was to move information to compile time in order to detect problematic usages and prevent them at compile time as much as possible. That talk had the overall mission statement: if it compiles, it works. But as you all know, it's not 2022 anymore, so this year's talk is going to be about compile time sparsity for vectors and matrices. And here we'll again follow an overarching design principle. This time we'll again move something, information, to compile time in order to save memory and runtime and to make sparse linear algebra code efficient by design. Meaning we also need a new mission statement, so it's no longer if it compiles, it works, but instead if it compiles, it's efficient. And I forgot to mention, if you have questions, of course, feel free to ask them during the talk. Now I want to start with a brief recap from last year's talk and explain what a Typeset Matrix is. Not too long, maybe 5 to 10 minutes, so that everybody is on the same page and you have like a talk that can stand on its own. So Typeset Matrices aim at moving semantic information to compile time. And examples for these semantic informations are physical units. So what does each entry in a vector matrix describe? Is this a position, velocity, or something else? And also information about the coordinate frame in which an entry is. So if you have different coordinate frames that your entry can be represented in, this is also part of the compile time information in such a matrix. Furthermore, there's an information about the type of matrix, so whether we have a covariance matrix, a Jacobian matrix, or a point in the mathematical sense, or a displacement vector. And all of this is done, or was done, to move the error handling to compile time, meaning almost all problematic use cases can be caught at compile time. The only thing that you could do incorrectly with that approach is sort of put in the wrong numbers, but all the math will be checked at compile time. And then, in the main part of the talk, I'll move on to compile time sparse matrices in C++. And here we'll aim at moving the sparsity from runtime to compile time. In order to fully benefit from that, we also have to move the loop iterations from runtime to compile time, meaning we need fold expressions instead of for loops. This means that today we forget the famous no raw loops and move to something even better, which is no runtime loops in the talk. Hope Sean doesn't hear that. Good. In the last section, I'll report several experiments that I did to answer the question whether we can get a free lunch with this approach by moving the calculations from runtime to compile time. A free lunch in that case would be that we are more memory efficient and as well as more runtime efficient. Now, as I said, Typeset Matrices, what I presented last year, aim at moving as much information to compile time as possible. And the first ingredient that we're going to use for that is what I call named index structs. These index structs identify each entry in a vector matrix with a unique name. In that case, dx stands for distance x. And we define that by inheriting from a base class. We specify in which coordinate frame it is. In our application, self-driving vehicles, it's often the vehicle rear axle coordinate frame, sort of the standard frame. We specify that this is the Cartesian x-axis in that frame, and we specify that this has a physical unit of meters. Same thing can be done in a different coordinate frame, so this would be the y position in the sensor frame. And all of these structs are, of course, can be defined by the user, so you could freely change all the names and the coordinate frames. That's up to the user. In general, these names are made up out of 3 parts. First part is the physical quantity, so whether it's a distance, velocity, acceleration. Second part, the axis, x, y, z. And the last one is the coordinate frame. Now I should also mention why that the x struct doesn't have a coordinate frame in the name. That's first of all for the presentation today to make it shorter, but we're also using that in production like that because the vehicle front rear axle coordinate frame is our standard frame. So these types are by convention without a suffix to have like short and good names for them. But as I said, everything can be configured. So if we're in a different project or so, we need different frames, all of this can be done. Then the Typeset Matrix class that I mentioned looks like this. So I don't want to go into details about the method. We don't need that for today. So the class has 4 template arguments. The first one is the scalar type, whether you want to have floats, doubles, integers in a matrix. The second argument and third are row and column index lists. So that's a type list of the index structs that I've shown earlier. And this describes sort of the content of the matrix, or what it physically means, an entry in that matrix. And as I mentioned, the last information piece that we're going to need is the matrix tag, which specifies whether we have a covariance, Jacobian, point, or displacement vector, and a few other options. And the only member in such a type-safe matrix is an eigenmatrix or any other underlying linear algebra library. And it simply has the scalar type that we specified, and we use the size of the row index list and column index list as the size of the matrix. Now this is an example how such a matrix would be created. This is a covariance matrix with 2 indices as rows and columns, x position and x velocity. And as I mentioned, we don't need many methods. The only thing that we're going to need today is actually the element access. So there are 2 ways, or 3. I'm showing 2 here, ways to access the elements. The first one is the preferred one usually, when you want to access the physical quantity, so a physical unit aware entry, then you call that coefficient SI method. And the important point here to note is that we always have to specify at compile time as a template argument what we're accessing. So here we're accessing the index dx and vx, and a position and velocity index in a covariance. You have to multiply the 2 physical units, which means you end up with a quantity of meters squared per second. So this is sort of the usual user interface, but there's also a slightly less safe way. You can also access the plain scalar values with the add method. And as we are today more implementing something low level, I'm only using that add method, but in general, the users usually would stick with the other methods. Any questions already? Or if not, I'll continue. This is sort of a quick overview of the main building blocks that we have. So we have a Typeset Matrix class that inherits from matrix base in a CRTP manner. And matrix base is the base class for all proper matrices and for all matrix expressions. And such a matrix expression has 2 template arguments. The first one is a promotion type. And this is only used at compile time to do all the compile time correctness checks that I mentioned. So this sort of infers the resulting template arguments of the new typeset matrix that is being created, and also does all the error checking. The second template argument, the linear expression, is an expression from an underlying linear algebra library, for example, eigen, and this is responsible for doing the runtime calculations. So we have 2 parts. One is the compile time promotion, and the second one is the expression that's actually doing the runtime calculations. Now, as I said in the beginning, we want to also represent sparsity today in the new talk, so we have to slightly modify these classes. And we do that by adding a functor to the typesafe matrix class. That functor sort of indicates or specifies at compile time which entries are 0 or 1 in our matrix, or whether an entry is remapped to another one and doesn't need storage. So, for example, in a symmetric matrix, or we can have all other kinds of remappings. And this also means we no longer have a full dense matrix. So several entries can be 0, so we can no longer use an eigenmatrix underneath and also not eigenexpressions. So we now need to use sparse expressions that are sort of tailored to our use case. But this is fairly simple, so you just need the regular additions, multiplication operations and so on. So that's not such a big effort. Good, now that's the last slide from last year's talk. I actually want to show how the compile time checks are done with typeset matrices. So here in this example, we have in the middle a covariance matrix. And that describes, as rows and columns, the x and y position and x and y velocity in vehicle frame usually, so there's no frame suffix, that's in vehicle frame. And then we multiply with a Jacobian on the left-hand side that goes from that vehicle frame to a sensor frame, and we multiply with the same Jacobian transposed from the right-hand side. This is usually the operation that you have to do to get to a different coordinate frame with a matrix. Now, when this is executed with a typeset matrix, then the first thing that is being checked is that the inner indices are actually matching up. So they have to describe the same physical thing. And if this is the case, and also the exponents here are identical, I mentioned that in a covariance matrix you have to multiply the physical units, and this is indicated by the exponents of 1. In a Jacobian you have to divide, so the exponent is -1. In a Jacobian, you divide the two physical units by each other, and this gives you the resulting unit. So if these indices are identical and the exponents are the sine inverse of each other, then this thing cancels out, and the column indices from the right-hand side move over to the covariance in the middle. Now the same thing is done on the left-hand side. They are identical, exponents are the sine inverse of each other. This cancels out, and the indices move over, and we now have a covariance matrix in sensor frame, and this is exactly what we're assigning it to on the left-hand side, which means this is a valid operation and it can be done. No compiler error will be emitted. In case we would sort of exchange the order here, put the transposed Jacobian on the left-hand side, or we have different indices, you would directly get a static assertion as a user, and it wouldn't work. Good, so much for the recap from last year's talk. Now we'll move on to the new content. So we're talking about sparse matrices, and first of all we should note that there are two different kinds of sparse matrices. The first one, most common one that you're probably familiar with, are runtime sparse matrices, where only at runtime you know which entries are 0 or 1. Well, ones are usually not represented with that, so it's mainly 0 entries, and that's only known at compile time usually. At runtime. And for compile time sparse matrices, the sparseness information is known at compile time. This might seem strange, but we will later see a few examples where this can happen. So this can happen due to physical constraints of the problem structure, or due to modeling structure. For example, if you don't want to model correlations between certain variables in a state, then you would also have 0 entries. And the overall goal is to not only represent entries that are 0, but also to be able to represent entries that are 1 or entries that are remapped to another entry in the same matrix. Now I want to show a few examples of these sparse matrices. The first set of examples are more what I call matrix shapes. So you could call that sparse matrices, but in general, I would think it's more a property of the matrix shape. So a diagonal matrix is probably the easiest one, where only the entries on the diagonal are non-zero. I hope it's visible. So entries in gray usually mean here on the slides that they don't occupy storage. An asterisk means an entry without any constraints, so just an arbitrary value. And you have 0, 1, compile time 0 and 1 in the examples. There are upper triangular matrices where only the upper triangular part is occupied, upper unitriangular matrices where the diagonal is 1, and of course also the lower equivalent of these, and symmetric matrices. Covariance matrices are usually symmetric, and here the lower part is sort of mirrored to the upper part, and you don't need to store it if you want to be efficient. Of course, it could also be the other way around, that you store the lower entry. Yeah, doesn't matter in the end. Good, then there are also proper sparse matrices. So an example of that would be something like that here, where you have diagonal blocks. So the off-diagonal blocks are 0, and on the diagonal we have two identical blocks. So the bottom right block, one second, is remapped to the top left. Yeah.
What is the difference between any runtime value and storage in the key, like the letters versus the asterisks?
Well, usually you have to have an arbitrary runtime value, otherwise you wouldn't need storage. Only the remapped one. So if you have a symmetry, then one of the two doesn't need storage, and the other one has a runtime value. So yeah. Yeah.
So I take it that these are more like they're templates to identify classifications of matrices that you're going to be using, so that you can pre-parameterize them, and these are just where the zeros are constant at compile time, and is that correct?
Yeah, sort of templates, but you're completely free to define the layout with a functor. So you can define an arbitrary sparseness structure. This is just the most common things that occur in practice. So I have an example for this one when it occurs. So for example, when you have a state vector in a Kalman filter, for example, that represents 2D positions and velocities, and you want to go to a different frame, then usually you need to multiply these with a rotation matrix, and it's the same rotation matrix usually. And then you only need to represent the rotation matrix. The off-diagonal entries are 0, and the lower rotation matrix is sort of represented by the upper left corner, and you don't need to store it twice. Then there are also even more general sparse matrices. This is another example. So here the off-diagonal blocks are again 0, and on the diagonal we have a 2x2 block that is symmetric. And this is, for example, used if you want to represent a covariance matrix. And let's say we don't want to represent correlations between positions and velocities, then you would directly end up with such a covariance matrix. So the things where you represent things, the non-zero entries are symmetric, the 2x2 blocks, and the rest is 0. So moving on to another real-world use case where this is suitable. So in the state transitions in a Kalman filter, so if you want to estimate the state of objects for example, self-driving vehicles, you need a state transition where you go from the old state to the new one. And then usually, if you have a constant velocity model, the new state, dx prime, is given by the old state, dx plus delta time times velocity. And if we put that in matrix form for a state vector that contains 2D positions and velocities, this would look like that. And yeah, almost all of the matrix is trivially either 0 or 1. And you have only 2 entries that actually get a runtime value depending on the time difference in your time step. Another example are measurement matrices in Kalman filters. So here, let's assume we have a fairly large state vector. That's the columns here with 3-dimensional positions, 2-dimensional velocity, 2-dimensional acceleration, and an orientation. Then the measurement of our imaginary sensor measures xy position, usually in sensor frame, and also velocities. This would lead to such a matrix here where only the 2 entries marked with the asterisks are actually non-trivial, and all the rest is 0. Now, before we come to the actual compile time representation of the whole thing, I want to explain how eigen represents runtime sparse matrices, just for a comparison to get a sort of rough idea about the differences. So in eigen, if we want to represent that sparse matrix here, the first thing that is needed is an array or a container of values, and this just stores the values column-wise. So it starts with 22, 7, and then continues with the columns. Then we also need an idea where the columns start in that array, and this is done with the column start array here. So this means that the entries in the first column start at index 0 and end at index 2 in the values array. So the end is exclusive, so the end doesn't no longer belongs to the column. So at 2 is sort of the start of the new column. And in order to be able to fully represent or reconstruct the matrix, we also need the row indices of these entry. So the 22 is in the first row, and the 7 is in the second row, which leads to a third array. And now it should already be fairly obvious that this is sort of overhead, so you need 3 containers to store that. At runtime, if you want to do operations on that, it's also fairly inefficient to iterate over that. It can be really efficient if you have huge matrices, so hundreds and thousands of rows and columns, then this is probably the only choice. But if you have smaller matrices, like in our application, 10 by 10, 20 by 20, this would be a huge overhead, and it just doesn't make sense to use such an approach for that. Then it's better to just use dense matrices and rely on SIMD optimizations instead. Good. Now that brings me to sort of the center slide of today's talk. So our goal today is to make all sparse matrix operations efficient. And we're mainly going to look at the most, or one of the most expensive operations, which is a matrix multiplication. So we're multiplying 2 matrices A and B. B, let's assume it's dense, so all entries are occupied. And A has a certain sparsity structure as is shown here. And this would result in a matrix C. Now when we want to evaluate the first entry of our matrix C, C1, we can just take the first row of A, first column of B, put it next to each other, and then we multiply each of the corresponding elements here together. And this leads us to C1 equals A1 times B1 plus A2 times B5. And then it gets interesting, because here we have a multiplication 0 times B9. And ideally, this would just disappear as a no-op and not appear here. And 1 times B13 should just be an addition of B13. So this would be sort of the ideal code that should be generated here. And then we need only 2 multiplications instead of 4 multiplications, which would be way more efficient. Now let's see how this looks in C++. A lot of templates here. So the most important thing to notice is we have a helper class here, matrix multiplication, and this gets a variadic template argument list. These are the pairs, so the cross product of row and column indices in the matrix are given as pairs here. And then we have a run method, and all that run method contains is a fold expression that sort of loops over all the entries in our matrix and calls another helper method that's actually doing the evaluation for these entries. And that calculate entry method here, again, has a fold expression further down, and we are folding this time over the inner indices. So this is sort of in the matrix multiplication, the multiplication unrolling over the inner indices. And we again have a simple fold expression here. We are adding all the multiplications of the corresponding entries and adding them together to the final result.
Are you targeting 17 or 20?
This is 17 mainly, yeah. Should all work in 17. Yeah, and this already brings us to our secondary mission statement. So we've achieved no runtime loops, so it's all fold expressions here. And we don't need to loop with a for loop over anything here. Good, now let's take a look at that last helper method that we're using, or helper struct, multiply 2 entries, run. Looks like that here. So that basically consists of a few if-const expressions. And the first condition that we have is when one of the 2 entries that we're multiplying is 0, then we're simply returning a 0. No multiplication has to happen. If one of the entries, if both of the entries are 1, then we return a 1. If the left-hand side is 1, we return the right-hand side. If the right-hand side is 1, we return the left-hand side. And now the only thing that's remaining is sort of the last case. If none of these are actually true, then of course we have to do the multiplication, and we're multiplying the 2 entries from the matrix. And now this already brings us very close to our mission statement here. If it compiles, it's efficient. Yeah?
So in doing this, right, you're effectively asking the question, right? Is this 0 versus 1? Because I have a more efficient multiplication. I know I'm multiplying by 0 or 1. But presumably that's something that the compiler would optimize, especially if it knows like that get entry is like possibly a context or a function, right? Like, is the is the compiler not optimizing in those cases?
That's exactly what we're going to see on the next slide. So if you just hold on for a second, there was a second question.
This doesn't do anything special with the remapped entries. Is the idea that for those we're just optimizing storage, we're not doing any?
Yeah. Well, in the element access in that add method, there's a sort of the remapping is considered. Yeah, so that's where it will be handled. And actually, in reality, I think even the remapping is handled in here. I simplified it for the slide. So yeah. Good. So yeah, I want to return to the earlier slide and coming back to Andy's question. Let's take a look at that fold expression. So we've seen that the multiply entries run returns 0 in certain cases. So we actually have a fold expression here that adds, I don't know, 3.5 and then 5 zeros. And now the question to you, what do you think? Is this being optimized away, or can this be optimized away by the compiler or not? So is addition with 0 an identity operation that can be completely optimized away? See, shaking head, why not?
IEEE floating point rules.
Yeah,
You have to do the addition.
Floating point rules. So minus, there's a negative and a positive 0. And if you don't play with floating point settings, then by default it cannot optimize that away, because minus 0 plus a positive 0 is a positive 0, meaning addition with a positive 0 is not an identity operation. Which means we actually have to modify it slightly. So we have to help the compiler and actually remove the zeros, so the entries that we know are going to be 0 from that fold expression down here. And only then, I just realized that last week when I thought about the slides and the questions that could come up, I said, oh, wait, is it really being optimized away? And that gave me another 10 or 20% performance benefit, because before it was actually doing the additions at least. Yeah, there were 2 questions at least. You were first, I think, or no? Here.
Question about the previous slide.
Mm-hmm.
Instead of this additional template get entry kind, maybe this template add could return a type that is an integral constant when the element is known at compile time.
That could be done, but then you would still have to convert it sort of to an integer, or does it have I don't know, does it have an automatic conversion?
It has
Okay.
this conversion tool itself.
Would probably also be an option. I'm not sure if it would work all the way through, but yeah.
Then you still need to do the remove it.
Yeah, removing.
Yes. But if it returns a special type, you can overload the operator to handle that removing.
Yeah. I mean, there are definitely different solutions. The important thing is you have to remove it, either play with floating point settings, which I wouldn't recommend in general, or yeah, you have to remove it. Yeah.
Sorry, go back to the last slide.
Yep.
Yeah. So my original question was do you actually need all of this, especially if you're going to do the removing of the zeros? Right, because each time you call this, you're this is instantiated for every possible index counter.
Yeah.
And so for each of those, the value might be known at compile time.
Mm-hmm.
This part might optimize correctly without the actual if.
Yeah, it's a good question. So the returning the 0 should be completely removable, I guess. That was sort of also code that I did before I realized I remove it. But then you should still have a static assertion or something in there, maybe to alert in case you would ever arrive there. So the 0 should definitely, isn't important. The 1 you probably still need. The other things is the compiler might optimize, but it's always, I think it's not guaranteed, and that's always a bad thing. So ideally, I want to have it guaranteed that it's optimized away in all cases. But yeah, I would have to investigate. Maybe it's even done by most compilers, but you never know. Yeah.
Well, if you instead of just returning the double values there, if you return just a type wrapper, and then you could have each one of them annotated, and then you could just grab the value from it when you wanted to do the operation inside of your fold. But then you also have that extra type information already with the value, so you can do all kinds of stuff with it because you know what that specific operation is.
Yeah, it's probably also possible. Yeah. So I think there are several ways to achieve that. Yeah, this is also fairly new, as I said. So I haven't optimized it completely. There are definitely different ways how this can be implemented. Good. Yeah, this is what I mentioned. If you have the element access, there's also like if const expr in there, not too important. So in case you have a 0 element, you return 0. In case you have 1, you return 1. Here it's actually important to do that because all the other operations like addition or so also rely on that here and can, in theory, optimize it away, but I haven't verified if it's done in all cases. And the remapping is also in the third if const expr, what you asked earlier. Good. Now I've used functions from matrix functors a few times. Now we should also see what such a matrix functor looks like. So first thing that you need in a matrix functor is a getEntryKind method. And this sort of specifies whether one of the entries is 0 or 1. In a symmetric matrix, in that example here, we don't have 0s and 1s, so it always returns k-normal. Then we need an indication whether an entry is remapped. That is given by the isEntryRemapped method. That returns true or false. And in case it is remapped, there's a remapped index pair alias template that specifies to which index it's remapped. In that case, in a symmetric matrix, it just switches row and column index and indicates that it's symmetric. Then there's also an inverse functor. We will see later on for what that is needed. And a Boolean is content identical. This is more for cross-checking when you do assignment. And you have sort of in the destination matrix symmetry, then you can use that to check whether in the source expression you also have a symmetry that's guaranteed at compile time. Good, now we come to the fancy part. So let's assume we have a matrix expression like that here. So we have a matrix, we multiply it with a physical quantity of 1 second, and afterwards we transpose it. I want to show what this does sort of in the type system. So we start off with our matrix, as shown down here. And let's assume the rows describe x, y, z velocities with meters per second as a unit. And the columns are just indices with index 0 and 1. So that means we have a matrix with column vectors in it. And just for fun, and because it makes a nice example, the entries in that matrix are all remapped to the first row. So the vector is actually second and third arguments are identical to the first argument because I want to make an example here. In general, that wouldn't make much sense, such a vector, I guess. So first operation that we're doing, we're multiplying with 1 second. And what this does, so it doesn't modify the actual values in the matrix, but it modifies what the matrix semantically represents. So it used to represent velocities, and now it represents distances or displacements because we've multiplied it with the duration, the velocities. Then we do a transpose operation on that matrix, and that simply swaps rows and columns. And this will now be needed for a larger operation. So we again have our expression here, and we want to evaluate that into a new matrix that again occupies storage. And for such a matrix that occupies storage, we need again a sparsity functor. But how can we determine such a sparsity functor? So it's just not realistic to let the user infer or manually define the sparsity for arbitrarily complex expressions that would immediately explode. So we need an automatic way to infer the sparsity functors for any expression. And here we want to see how this is done. So let's assume we want to know what the remapping of the red A in our source matrix up here is. Then we first of all have to invert the operations that we do in our expression here. So the inversion of a transpose operation, that's really easy, is another transpose. So we're transposing the matrix. Then the inversion of a multiplication with 1 second is a division by 1 second, which brings us back to our original indices in the underlying matrix. And now we can query the sparsity functor in the underlying matrix. Hey, what is this red A remapped to? And that says, okay, it's remapped to the first entry that's actually occupying storage. And then we can go up again, like in the forward manner. We're again multiplying with a quantity of 1 second. This modifies the indices. We see the A entry green is still at the same position. Then we're doing the transpose operation. And we now see that the green A ends up in the top left corner. And this now gives us the full remapping of the resulting matrix. So we now have the remapping of the red entry to the green A in the top left corner. Yeah, it's a fairly big operation. And the way from the top left to the bottom right, this will be done by our functor that we sort of create while we evaluate the expression. And from the bottom right to the top right, that's actually the inversion. We need the inversion of the functor for that. And that's why we have that inverse functor. I will show on the next slide how this is being created on the fly. Yeah.
I'm curious why seconds are in like square brackets.
Yeah, this is often the notation for like physical units, that you have square brackets around physical units in.
Why not the literal?
Oh, well, this is not like real C++ code. So imaginary C++ code. So at least the physical unit in there, yeah. Yeah.
So the mapping in the bottom right still has to be defined.
Yeah, this is sort of in the underlying matrix, in our MET matrix here, that's sort of at the core of the expression, and this does exist somewhere, so it occupies storage. And in order to create it, you must have given it a functor. And this is sort of what we have, but we don't have functors for any expression that we create from that. And sort of this here now gives us the new sparsity functor for the new matrix that we created, so the result matrix.
So all like the leaf expressions need to have their own individual functors, but
Yeah,
everything else.
anything with storage needs to have a functor. Yep. Good, now let's see how we can invert a sparsity functor. First of all, the translation from our almost C++-ish code, with the exception of the square brackets here, to a matrix expression looks like that here. So we have a matrix that has a storage functor, as I mentioned, because it occupies, well, a sparsity functor actually. It occupies storage, so it has a sparsity functor. Then we create an expression for the multiplication with a unit, and another expression for the transpose operation that we're doing. And then we want to evaluate the inverse functor for this thing. And this is done by simply writing, sort of imaginary writing, our whole expression here. And we access the inverse functor member alias of that thing. And now what this does graphically, we're splitting the left part, left of the colon, into an outer blue part and an inner orange part. And the outer blue part is moved to the right-hand side of the colon, and the orange part stays. This is the first operation. Then this is recursively repeated. We split it into outer and inner part. The inner part moves to the right-hand side of the colon. And now we're already at the storage functor. And for a storage functor, the inverse functor is just an identity functor. So we end up with the right-hand part. And this is sort of the inverse of our expression. With one caveat, as I said, the inverse of multiplying is dividing. So to be 100% correct, it's actually a division operation. So we have to multiply the multiplication, sort of modify the multiplication to be a division here. And then we can use that, as I showed on the previous slide, to sort of evaluate the whole thing. Good, now on that slide I have a few questions for you. First of all, let me explain what we see here. So the question is, we have a matrix assignment. We're assigning a matrix B to a matrix A. In matrix A on the left-hand side, on the diagonal, we have arbitrary entries marked with the asterisk. And on the off diagonal, we have a sort of symmetric entry that's remapped to the top right. And now the question for you is, which of the assignments here, the 5 different assignments that we have, are actually correct? So when can the left-hand side represent the right-hand side? So first question, when we have something like that, I should mention question mark means we don't specify anything about the entries. So if we have off-diagonal entries marked with an asterisk that can have arbitrary values, can we assign that to the matrix on the left-hand side?
No.
No? See, shaking hands. We cannot. Because, yeah, the left-hand side has identical entries there, and if we would have a 3 and a 5 on the off-diagonal, this can't be represented by the left-hand side. Next example, can this be represented by the left-hand side? Yes. I see nodding heads. It can. And this one here?
Yeah.
Yeah, it can also. And this one here? Yes, it can be represented, so the code is correct. Last one. Also, yes, good. So that means we've sort of ensured the correctness. We can emit a compiler error, a static assertion for the first one, and then we've achieved sort of our mission statement from last year. If it compiles, it works. But we want to do more, as I said. The question now is, which of these assignments is actually efficient? So the first one is incorrect. We don't have to look at that. Is the second one efficient? So are we sort of preserving the sparsity as much as possible? I see nodding heads, so yes, this is efficient. What about this one here? Also yes. Yeah, it has sort of the inverse remapping. That's also efficient. And what about this one here? I see no's. Why not?
Zero value.
Yeah, there are 0 values and we're sort of dropping them and putting it in just a symmetric value, so we're losing actually sparsity. So this is something that should be forbidden and lead to a compiler error. Yeah?
Can we go back to the second one then? So the question mark means that could be anything. In particular, the question marks could be fixed 0 or 1, right?
Yeah,
And so
okay.
we're
Yeah, in
losing
that
sparsity
case, you would lose sparsity information. So in that case, question mark means ignore the thing. It's not part of our quiz.
Okay.
Yeah. I'm changing the rules afterwards, but yeah, nice observation. Good, so did we have the last one already?
No.
Okay, what about the last one? Not efficient, why not?
Dropping information.
Yeah, because we're again dropping the 0 and 1 on the diagonal, so that's also not efficient. And this means if we emit static assertions for these two, we've come as close as possible to our mission statement. If it compiles, it's efficient. Now, that sort of concludes the first part of my talk, or the bigger part. And in the second part, I want to answer the question, or come to the statement, there's no such thing as a free lunch. You probably all know it. And I want to investigate whether this is actually true and applies in our case, or whether we are lucky and maybe are getting a free lunch, meaning less memory usage and more efficiency, runtime efficiency. To answer this question, I did several experiments. So the first one is a matrix multiplication of 3 matrices. So we have an upper triangular matrix U multiplied with a diagonal matrix D, and then multiplied with a transpose of the exact same upper triangular matrix U transposed. And I'm going to evaluate how much time this needs. So there are usually textbook algorithms that make use of this sparsity information. So from numeric textbooks, you can take that and it already reduces the amount of operations being done to the absolute minimum. So the diagonal matrix would then usually be represented with a vector. And it also only accesses the non-zero entries because it knows, okay, this is a upper triangular matrix. In the middle, we have a diagonal. And on the upper right, triangular matrix transposed. Now, if I compare my approach with that textbook algorithm, then the chart looks like that. So we have on the x-axis the matrix sizes. It's always square matrices, and we go from 6 by 6 until 24 by 24. And the y-axis is the runtime. And you can see that it's, in some cases, especially in the really small sizes, I have a zoom in on the next slide, giving a big benefit. I'm not sure why it's not that much benefit for 12 and 14, but the higher up the numbers go, then you again have more benefits. So for the small numbers here, you can see it's 50% or so faster than such a textbook algorithm, so it's definitely worth doing that. In the next slide, I also want to compare it with Eigen in different versions to see how it fares there. So this one here is a bit of an unfair comparison. I mentioned earlier that Eigen has...
I have a question. Was this like using a special annotation that said that this was a triangular matrix, or was this just using the code that falls out of the rules that you built before?
Well, the annotation is in the sparsity functor, and what I usually also do, if you know that you end up with a symmetric matrix as a result, we see that later in the experiments, then you don't have to evaluate like the full matrix, you can only evaluate one part of it and the other one falls out of it. That is also being used in certain cases. So I'm not doing like a dumb matrix multiplication also because of compile times. So it's more efficient if I know I don't have to do it for all entries, then of course I'm trying to reduce it as much as possible. Yeah.
And for the textbook entry in the graph, do you use vectorization?
No, only, well, I didn't check, maybe the compiler auto-vectorized, but I don't think so. It's runtime loops, a lot of runtime loops with different indices also. Because of the triangular structure, you sort of have the loop gets smaller and smaller. So I don't think it would have vectorization. We will see later in the eigen example, eigen has vectorization. There we'll definitely see how this compares to vectorization. So, yeah, you were first, I think.
So, what is your solution doing that the textbook algorithm isn't? I would have expected your approach to at best sort of automatically accomplish what the textbook algorithm accomplishes by hand coding.
Yeah, one difference is, for example, I don't use runtime indices, so everything is known at compile time. So even in a normal matrix library, you would say, okay, I want to index 3 and 5, and the indices come from a loop variable in a for loop,
Okay.
and that might be difficult to see for the compiler. And in my approach, the compiler knows the offset for that 3-5 element is, I don't know, 15 or so. So that's one offset that the compiler sees, and that already can give a benefit. Plus, as I said, if the result is a symmetric matrix, I'm also trying to make use of that. But I think that would be the same for that algorithm. Yeah.
I guess similar to Jeff's question, I think if you were to take the textbook algorithm and like force unroll all of those loops, right? Because the extents are known at compile time.
Mm-hmm.
To actually do that, do you know what the difference would be like in that stuff? Like, is that the only thing that this is doing, or is there something
Yeah,
else
I
going
haven't
on?
tried that, like unrolling the textbook algorithm. Yeah, I can't say.
It's like you're unrolling the loop, right?
Yeah, the loop unrolling, yeah. So it might make it easier for the optimizer, especially in that case where it's not like, is it not a dump loop over like matrix multiplication, but an intelligent loop, and that's probably difficult for optimizers, I would guess.
Probably branches as well, right?
Yeah. Good. And as I said, we had that runtime sparse matrices from eigen earlier, and just for fun, I compared the runtime sparse matrices from eigen with that. That's of course a bit unfair comparison, but you can directly see that it's like orders of magnitude higher the runtime. And in the next example, of course, I will switch to SIMD eigen as a comparison, because that's probably a fairer comparison. So the second experiment does again a similar matrix multiplication. So we're multiplying AB times A transpose. The inner matrix, the middle matrix, is symmetric. And the outer matrices, so they are identical. It's the same matrix on the left and right hand side. And for that matrix, I vary the sparseness from 0 to 90% in the experiments to see at which sparseness level this sort of is better than eigen with SIMD operations. And of course, this thing will result in a symmetric matrix. So this is also something that I'm making use of. That was the comment earlier. So I'm only evaluating what is needed if I know the result will be symmetric in the end. So this here are quite a few lines. Maybe focus on the red one. This is sort of the eigen benchmark, what eigen needs. And the other plots are like sort of in increasing order of sparseness, what the runtime of my approach is. I will also zoom in later to the smaller areas. But you can see that the larger the matrices are, the better the SIMD eigen approach probably fares. But even there, if the sparsity is 50-60%, then they're on the same level. And as soon as sparsity is higher, of course, it's faster. And now, as I said, I want to zoom in for the smaller sizes from 6 to 12, which is usually what we have in our problem space, so we often have, I don't know, 8 to 12 by 12 matrices. There you can see that even with 0 sparseness, it's faster than eigen in many cases. And starting from 12 or so, eigen starts to become faster. And it's also faster for 6 and 7, but only for 10 and 20% sparseness. Or no, for 0 and 10% sparseness, I think. Yeah. So as you can see, it definitely makes sense to do that. Of course, you have to measure in reality what it gives you. And it depends on the sparsity, what you have exactly, but it's definitely an approach that's worthwhile to use, and it can bring even big benefits. So if you have really sparse matrices, then it can bring a really huge benefit. And on the other hand, it enables you to still write matrix calculus in your C++ code, which makes it really easy to understand, while at the same time giving you all the runtime benefits that a hand-tailored or a handwritten method would give you. Now in the third experiment, another operation again, 3 matrices that are multiplied. This is from a specific Kalman filter implementation where we have an identity matrix. From that we subtract the product of a gain matrix, that's usually a full matrix, with a measurement matrix, and the measurement matrix is fairly sparse, as can be seen here. We multiply that with a symmetric covariance matrix, and on the right hand side we again multiply it with the same term transposed. Now I have later on 2 different plots. So in the first plot, I'm only using sparse multiplication for the inner multiplication. So the gain times the measurement matrix. This is sort of the first thing, if you only use sparse multiplication for that. And in the second experiment, I propagate the sparseness all the way through the expression, meaning the identity matrix is fairly sparse. It's completely trivial. The subtraction with the other sparse matrix gives another sparse matrix, and this is then multiplied with the covariance. And here I have bar charts. So the left-hand side is with floating point numbers, right-hand side with double numbers. The purple bar is a simple loop, so just a dumb matrix multiplication like you would write it, a for loop for the multiplication. That's sort of the baseline. Then in green we have the eigen multiplication. Blue, light blue, is what I explained earlier. Only the inner multiplication is done in a sparse way, and the orange bar chart is then like fully sparse multiplication all the way through. And you can see that this is almost 50, more than 50% faster than what eigen does. I mean, the matrices are fairly sparse, so you might I don't know, maybe you expect it's even more, but it definitely brings a large benefit. Yeah.
These comparisons that you're doing, are they using the code like that you had presented last time, just without the compile time feature in it? So it's all of your code is doing the correctness check, and then you're testing that code at runtime versus what you've done to add this compile time.
So in the experiment, the numbers here are from my verification code on top of eigen, but I also ran the plain eigen numbers, and they're, I don't know, 1 or 2% difference or so maybe. Sometimes even the wrapping is faster. So they're on par, so I also checked plain eigen. Yeah?
This is probably an ignorant question, but it just occurred to me that addition and subtraction are probably generally going to have to discard the sparseness of the 1 entries, right?
Because it's also not.
Unless you're adding 1 and 0, or
exactly. So if you're
adding 1 and 1, or
there's also no mechanism to do what you said, like 1 plus 0. No, I think that would also be, I would rely on the compiler to optimize, because addition is usually not that expensive. So the most important thing is the multiplication, and for the other thing, of course you could also construct similar things. But then, it probably becomes a big goal.
I'm not thinking so much about optimizing the addition itself. I'm thinking about the fact that you lose for the result of that operation, you lose the sparsity. And
but as soon as you add a runtime value to a compile time known value, it's a runtime value. Yeah.
Right.
Yeah. So.
But also, like in practice, this probably doesn't come up very much, I would guess. the matrices that you would have where you know there are ones, say, like on the diagonal. This is typically because you're doing like a change of basis thing, and you wouldn't add two change of basis matrices.
Yeah.
In theory, you could, but like it doesn't make sense conceptually.
Yeah. Yep.
So you consider using like integral constants so that you have additional describability as opposed to like just describing 0 and 1. Like you can do compile time computation.
Yeah. No, I haven't tried that. Well, also because we don't have a use case that an entry is fixed to 5 in a matrix. Well, it could occur in these transitions. You could sometimes have like I don't know, 1/2, like if you have accelerations or so, it's time square or something, and 1/2 in there. I haven't investigated that, because we rarely occur it. But it could be done. The integral constant could also be used to do the indexing that I'm doing with the index structs. That could sort of, in principle, also be done with integral constants, but then you would lose the expressiveness. It was just, I had that approach, and this sparseness thing fit right into it, so I thought I'll implement it on top of that. Good, then maybe one point to note, how is this related to std MD span? Because sometimes MD span is also could be used for sparse matrices. In MD span layouts, they map integers ij, and if you're higher dimensional, more indices, to a storage location. But the big difference to what I'm doing is that the actual access in an MD span is done via runtime integers. So it's not a compile time value that you can actually use to do these kind of things. And my sparsity functors provide information that can be used to map index types, or, as I said, std integral constants to a storage location. So they're a bit similar to these layout policies. They're sort of the input from which a layout policy in my approach is inferred. And as I said, the element access is always done with compile time indices. I needed that for the physical quantities because each of these accesses can return a different physical quantity. And here, I'm using it to do these optimizations and know at compile time if it's 0 or 1. Good, that already brings me to the summary. So in the talk, we've combined memory efficiency with runtime efficiency. So in our case, there is such a thing as a free lunch, but of course, as always, restrictions apply and fine print. So you should always measure. It can make sense depending on how sparse everything is. Whether you can use SIMD operations. Of course, if you don't have SIMD available, then you would probably immediately get a benefit. But if you have SIMD operations from Eigen or a linear algebra library, then of course it makes sense to benchmark and check at which sparsity you get an actual benefit from that. The precondition to achieve that is that the iteration is actually moved from runtime to compile time, which is why we sort of ditched the no raw loops for today and moved to no runtime loops. And with the approach that I've presented, we can enforce at compile time both sparsity correctness, which sort of is the mission statement from last year. If it compiles, it works. And at the same time, we can also enforce maximum sparsity efficiency, which is our overall mission statement from this year. If it compiles, it's efficient. And now I want to skip that one. And as we still have time, I'll also report about the compile time. That's probably the next question that would come up. So let's see how that compares. This is not for a single matrix multiplication. This is sort of for my whole benchmark set, but it gives a nice impression how it increases with the number of elements. So in green, in purple, that's the number of entries in the matrices, and in green, this is the compile time in seconds for my whole benchmark set. And you can see that with a size of 24 by 24, we already end up with 10 minutes compilation time. So it's fairly significant. As I said, it's like 15 or 20 benchmarks. So if you're just doing a few matrix multiplication, it would be a lot less. But still, you can see it's probably cubic here. The compile time and the number of entries is a square term. So it works until 20 or maybe even 30, but at some point it breaks down. And I also had to do certain measures to become as efficient as possible with the template metaprogramming. So I have type lists, and you have to extract elements from type lists. And there I played around a lot with how this can be made as efficient at compile time as possible. You might know the talks by Odin Holmes about metaprogramming, where he used template aliases. These are probably almost the fastest solution, but really difficult to write because you can't use partial specializations. I realized at some point that variable templates also make a really nice metaprogramming facility. So you can use sort of the decal type of a variable template to merge type lists and things like that. So this seems to be as efficient as the aliasing approach. So it's really nice, as fast as the other one, but you can use partial specializations for that, which makes the code better to understand. Unfortunately, it seems that the C++ standard mandates that variable templates are actually, the types are actually instantiated formally. I think neither GTC nor Clang do it, but the standard seems to suggest that it's mandatory to instantiate them, which is why I'm slowly moving away from that, because ideally I wouldn't want to have incomplete types even for this variable template approach. That would be the ideal solution. So if anybody knows why this instantiation or the types have to be complete for these variable templates, I would be really interested to hear that, if it's something that can be removed or there are other conditions why it has to be like that. Yeah, I'll ask around at the conference. I hope I find someone who knows it. Good, that's it for now. I thank you for listening and looking forward to your questions. We still have time.
Given the compile times, what's the developer workflow that people have? Are they mostly iterating on these expressions and in a dynamic language, and then translating it and just hope to get it right once and compile it, and then don't iterate on it in the C++ side, or how does that work?
No, usually the expressions that you use here, it depends. If you develop something from scratch, then it changes a lot. But if you're in a slightly more mature state, then you don't change that much. So it's fairly consistent. And I should also mention this is, so the compile time checking from last year, this is used in production with us. But this here was sort of my work in the last 2-3 months that I did on the side. So it's a first implementation. We're not sure whether we are going to activate it, because you probably have to use it everywhere or do some interoperability. That's also possible. But if we would want to use it everywhere, then it would be a bigger work package to replace that. I still have my library interface on top of it, so the interface sort of stays identical, but you would have to specify all these sparsity functors for your matrices. So a bit of an effort to convert that. Another question? Yeah.
Yeah. So they have a SIMD presentation on Monday once.
Yeah.
Yeah. Did you go to that?
No, I arrived Monday after that. Otherwise, I would have been really interested. Yeah.
And maybe if you watch the video, you might try applying maybe some of the standard SIMD.
Yeah. I also thought about that. It might make sense, because I probably also know at compile time, there are 4 entries that I'm going to multiply. This is a SIMD operation. Of course, it has to be aligned maybe to something, but this is something that's definitely interesting. And what's really nice, if I have the index structs that name my entries, I can do an arbitrary reordering of my columns and row in matrices. Then you get lots of compiler errors, because you always have to mention the indices. But if you fixed all your compiler errors, the code is almost guaranteed to be correct again. So reordering of some things, what used to be I don't know, month-long thing, if you wanted to do that with eigen, and you probably have several bugs left afterwards, that's fairly simple with that approach. So if I know, for example, I have these sparse matrices, and there are, I don't know, the first 3 columns have entries, and then there are a few scattered ones in the back. I could just reorder that, move the non-zero ones to the front, and then hopefully benefit from more SIMD operations. You were first, I think.
So do you have any recommendations for how to make those compiler errors meaningful to people?
Yeah, there you should watch my talk from last year. I implemented something to make it meaningful, even with that's doable without concepts. I implemented it for C++11 already. Concepts could also help, but what I produced, like the error messages that are produced, are almost identical to what you can get with concepts. So I had these promotion types that I showed in the beginning. These are empty structs, and they inherit from a few base classes, and each of these base classes is a requirement, sort of a small concept-like thing, and that has a static assertion in it. And if that fails, you get the full instantiation history. Like you say, okay, that I have an addition promotion that failed, then this addition promotion required that the indices are identical, and there you had the static assertion, and then in the instantiation history, you can almost, yeah, it's still template errors, but you can read, similar to template, to concept error messages, what caused the actual problems. And you can also build checks from smaller checks, so compound checks, that's also possible. And I also had several other checks that I explained. You can sort of check aliasing if the left-hand side and right-hand side in a matrix equation aliases. This can lead to incorrect operations. This is something that you can check at compile time. You can have dangling references in eigen. If you use auto together with eigen expressions, that easily leads to dangling references. This is also something that I tried to prevent with playing with R values and L values, and overloading all the methods for L and R values. And then you can check whether you have a matrix expression that's used as an L value. And if that is the case and you call anything on that thing, you would get a static assertion. It's not 100% equivalent to what eigen does, so you can't sort of have variables that store expressions, but we rarely need that, or I've never seen a code in our code base that does it. So, and there's even another more elaborated possibility. You could sort of pass the whole expression tree and check whether, like if you mark if something contains a reference to a matrix, then you could sort of pass your expression tree and check whether such a reference is in there, and only fire an assertion in the correct case. But watch my talk from last year. Yeah, Andy?
So I'm wondering if you can push this even further, in the sense that I imagine a common operation is like A times B times A transpose, or during this sort of change of basis. And if you phrase it that way, you actually have two multiplies, and you've made those multiplications as quick as they can possibly be. Yeah. But there are two multiplications, when in reality, you know that this is a change of basis operation, and you have information about A, and so you can like hard code that particular change of basis, right? If it's like a triangular matrix.
Yeah, that might even be a more efficient possibility to do it even better. Yeah. I haven't tried that yet. You?
So this might be another question for your talk from last year, but have you thought at all about whether it might be feasible to instead of rather than just make the error messages clearer, if when you change the order of rows or columns, have it just work?
Yeah.
Like the API,
I think that
isn't really significant, right?
Yeah, in many cases it's not significant, but yeah, it has pros and cons. I didn't want to do many operations under the hood, so in our use case, you want to be as safe as possible. That plays into the safety talks. Like the whole thing from last year was actually about safety, preventing all errors at compile time. And then it's also good if you don't do much under the hood. So for example, if you would have I have a block operation that can extract a block from a matrix, and you're right, I could also, if it's not a non-contiguous block, so you're accessing rows, columns 2, 3, and then 5, 6, I could sort of do that. I have an operation for that, but it shouldn't be called block in my opinion, because this gives the user the impression coming from eigen that it's actually a block. So I would prefer to prevent it in that case, but it's definitely possible. So we have operations like that you simply can pick arbitrary entries from your matrix that you need and all of that. And also do automatic conversions between different state representations this is something, that whole approach enables several other things. You could do automatic derivatives, calculating from that. If you know it's a x position and x velocity, you can sort of, you know the derivative of these two entries in any Jacobian matrix where they occur will be that given thing. So you could automatically generate derivatives for Jacobians if you want to. We're not there yet, but we have a few extra things on top of that. Okay, there were more questions. I just don't remember who. Oh, yeah.
So I actually missed your first half, so I'm not sure if you mentioned this, but like, do you think it's possible to incorporate sparse information at a compile time when sparse information is kind of like varied, but I know the pattern in which it's varying? That's something like I often do with my data that I'm using.
So you mean you know the pattern in which it varies at runtime?
No, at compile time itself.
What do you mean with a pattern, like that it's a regular pattern in the matrix, or?
No, like the sparsity fact, like sparsity itself varies. So if I want to store a matrix and I know that for sure, I know it's sparsity. But then I want to, then I get like the same type of matrix, but the sparsity is different. But I know like it's just incremental.
Okay, I think we have to talk in detail afterwards what you exactly mean. I didn't get it completely. So you definitely can have like different sparsity for the same matrix content, but general something is off if that would happen. So if you have the same physical content in a matrix, then usually the sparsity should be identical unless you have different modeling choices. So if you, in one case you want to model certain correlations and in the other case you don't want to model, then of course you would have different sparsities for this matrix. Yep.
So I know that you mentioned like SIMD multiple times and that you should always like benchmark to make sure that you're actually getting performance improvements. But like a lot of the numbers that you're benchmarking against were like a plain just simple implementation, I'm assuming, like a naive runtime implementation, but like a fully optimized SIMD implementation.
Well, the eigennumbers were SIMD, so.
Okay.
The red line that I showed in that huge plot with the many lines, that was sort of eigen using SIMD. That was sort of a SIMD baseline. If you work with dense matrices, of course. If you have sparse matrices, then probably SIMD won't work. But eigen, and eigen also uses probably aliasing and padding at the end, so a few more things. It's not just doing SIMD things.
Is there some way that this framework could incorporate SIMD if it notices?
I would think so, You can either rely on the auto-vectorizer by the compiler, but that's definitely a way. I know at compile time which entries are 0 and non-zero, and then you would have to sort of not use a fold expression, but instead sort of infer, do I have a 4 or 8 block of multiplications? And if that is the case, you could emit SIMD operations, but I'm not sure how it would work if you have like sort of one SIMD part and then, 2 individual entries and then SIMD again. I'm not sure if that helps in the end, but it's definitely worth a try.
I feel like the biggest problem there is figuring out how to order your data so that the SIMD operations work. If you get that right, the compiler will probably be able to figure it out since it's straight line code.
But I mean, you could even do it programmatically, like you have a description of which entries are 0 and 1. Then you have your matrix description, and then you could write a small program, if you don't do it by hand, small program which shuffles the thing as many times until it finds a suitable optimization. Good. Any more questions? If not, then I would say we'll end early, go happily to the barbecue. And thanks everyone again for listening. If you have questions, find me at the barbecue or right after the talk. Thanks a lot.